Hi, Mr. Richards here. Today's algebra lesson is on simplifying radical expressions, and our first step is to make sure we understand what a radical expression is. And it is an expression that contains a radical. Okay, well, that might not be much help, but this might. Such as a square root. And that's what we'll be working today. A radicand is in simplest form if the following three conditions are true. First, no radicands have perfect square factors other than 1. Second, no radicands contain fractions. And third, no radicands appear in the denominator of a fraction. And one of the properties we can use to simplify square roots is called the product property of square roots, which states, for any non-negative real numbers a and b, the square root of a times b is equal to the square root of a times the square root of b. So we can basically take the square root of ab and break it apart into the square root of a times the square root of b, as long as they're both greater than or equal to 0. Our number example, the square root of 4 times 9 is 36, or 6. Or we can say the square root of 4 times 9 is the square root of 4 times the square root of 9, which is 2 times 3, which is also 6. So that's one of the ways we'll be working with our square roots, our radical expressions, to simplify. So simplify the square root of 52. Well, if we look at the prime factorization of 52, you may need to make a factor tree to get started. 52 is 2 times 26, and 26 is 2 times 13. And so the prime factors of 52 are 2, 2, and 13. So you can simplify this by saying, okay, 52 is equal to 2 times 2 times 13. Well, 2 times 2 there is kind of what we're looking for, because that's 2 squared times 13. And if we break this apart one more time, this would be the square root of 2 squared times the square root of 13. Well, the square root of 2 squared is just 2 times the square root of 13. And we can write this simplified answer just kind of together without the sign, 2 times the square root of 13. Now, what about another one? A little bonus example here. The square root of 45. Let's simplify that. Well, if you could see 45 as being the square root of 9 times the square root of 5, you may not need to break it all the way down in the prime factors, because this is really the square root of 9 times the square root of 5, and the square root of 9 is 3 times the square root of 5, which simplifies into 3 times the square root of 5. Now, what about simplify the square root of 2 times the square root of 24? Well, what is the square root of 24? How can that be broken down? Well, perhaps if you still need to, you could still make your factor trees 2 times 12, 2 times 6, 2 times 3. And if you need to take the 5 or 10 seconds to really break it apart so you can get these correct, do it. So we'll have the square root of 2 times the square root of 24 is 2 times 2 times 2 times 3. And what if I break these all apart so I can then regroup them next? The square root of 2 times 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 the square root of 3. Well, if I take these two square roots of 2, this is the square root of 2 squared. If I take these two, it's the square root of 2 squared, as 2 times 2 is just 2 squared. And then we're left with the square root of 3. Well, the square root of 2 squared is 2. Square root of 2 squared is 2, and still have the square root of 3. So this breaks into 4 square roots of 3. And again, this lesson's chock full of bonus examples. What about the square root of 5 times the square root of 35? Well, if we break this 35 into the square root of 5 times 7, we can then have the square root of 5 times the square root of 5 times the square root of 7. Our square roots of 5 we can group together into the square root of 5 squared times the square root of 7, so just 5 square roots of 7 is our solution. Now, we can also use absolute value. Now, what if we have an expression such as the square root of x squared? Well, does this equal x? Certainly seems to for whole numbers. Now, what if x was equal to negative 4? Well, we would put this in. Square root of negative 4 squared should equal negative 4. Negative 4 squared is 16. And the square root of 16 is 4. Does 4 equal negative 4? Well, no. And so we need to make sure, we need to do something to ensure a non-negative result. And the way we're going to ensure a non-negative result is by following the following rule. If the exponent inside is even, and then this results in a simplified exponent is odd, you must use absolute value. For example, the square root of x squared is actually going to equal the absolute value of x. The square root of x to the fourth, this is x squared. Well, that's an even result from an even exponent, so we don't have to put absolute values there. But if we had the square root of x to the sixth, when you take square roots, it's the same thing as multiplying your exponent by 1/2, so this would be x to the third. But since you had an even exponent on the inside and it simplifies to an odd on the outside, we need, once again, the absolute values. Now let's see how this works in practice. If we have the square root of 45, a to the fourth, b to the fifth, c to the sixth. What this is going to equal, if we take apart our 45, is 3 times 3 times 5, that's the 45, times a to the fourth times b to the fifth times c to the sixth. Well, this breaks apart now into the square root of 3 squared times the square root of 5 times the square root of a to the fourth times the square root of b to the fifth times the square root of c to the sixth. Square root of 3 squared now is 3. We cannot simplify the square root of 5 anymore. That's the square root of 5. Now, the square root of a to the fourth is a squared. And we went from an even on the inside to an even on the outside, so we do not need to use absolute value. Now, b to the fifth. Now, the b to the fifth can really be broken down into the square root of b b to the fourth times b. And the square root of b to the fourth is b squared times the square root then of b times, if we take our 6 1/2, that's 3. And this is going to be then c to the third power. But since we went from an even to an odd, we need to use the absolute values. And so when I go to simplify this, let's group all our non-square root, non-absolute value things first. So this is going to be then 3a squared, b squared. Now we'll bring in the absolute value, c to the third, and then lastly our square roots, the square root of 5b, and we can push that back together. And that's our solution, 3a squared b squared times the absolute value of c to the third times the square root of 5b. And again, for our bonus example here, what about the square root of 32m squared n squared c? Well, if we break this apart then, the square root of 32 is the square root of 2 times 2 times 2 times 2 times 2, it's 2 to the fifth, times the square root of m squared times the square root of n squared times the square root of c. Well, I can take my 2's and break it into groups of 2. So I could have the square root of 2 squared times the square root of 2 squared, and then I'm still going to have just one left alone, square root of 2. And then times the square root of m squared, n squared, and square root of c. Square root of 2 squared is 2. Square root of 2 squared is 2. Then I still have my square root of 2. Now, m squared, that's going to be m. But I'm going from an even to an odd, because 1 is an odd. That's just absolute value there. Then times the absolute value of n. Square root of c cannot be simplified, so it's just the square root of c. And so now I can push this back all together. 2 times 2 is 4. Then I'll have my absolute values, m times n. And then my square root 2 with the c. And that is my solution. Now what about rationalizing the denominator? This is when you multiplying the numerator and denominator by a factor that eliminates radicals in the denominator. Please remember, for these to be simplified, you cannot have a square root in the denominator. So we have our example here, the square root of 3n over the square root of 8. And now to rationalize the denominator, we need to multiply by the square root of 8 on both the top and the bottom. What this gets us then, on top, the square root of 24n, as we can take the 3 times 8 to get 24, over the square root of 64. Now something cool kind of happens, because you're left with the square root of 24n for now, over the square root of 64 is 8. So we've successfully rationalized the denominator. We've gotten rid of the square root. It's now a rational number. But we need to now simplify the square root of 24n. And the way we can do that, let's take apart our 24. 24 can be broken into, say, the square root of 2 times 2 times 2 times 3 times n over 8. Now, if I just take the 2 times 2, that's the square root of 2 squared times the square root of 2 times 3 times n. over 8. Well, the square root of 2 squared is 2. And then 2 times 3 on the inside there is just going to be 6n over 8. Now just when you think you're done, look at the 2 and the 8. That can be simplified one step further by dividing by 2 on top and bottom. So you're just left with the square root of 6n over 4, which is our answer here at D. And the last part of our lesson involves using conjugates. What is a conjugate? Well, something like A times the square root of B plus C times the square root of D, or even A times the square root of B minus C times the square root of D. Now something kind of cool happens when we use conjugates. If we look at something like 3 plus the square root of 7 and 3 minus the square root of 7, those are technically conjugates. Now what happens if I were to multiply these together? I would have 3 plus the square root of 7 times 3 minus the square root of 7. If you were just to FOIL these out, 3 times 3 is 9. 3 times the negative square root of 7 is minus 3 square roots of 7. 3 times the positive square root of 7 is 3 times the positive square root of 7. And then lastly, the square root of 7 times the negative square root of 7 is going to be minus 7. Now, these happen to cancel out. Minus 3 square roots of 7 plus 3 square roots of 7 cancels. And so we're left with just 9 minus 7, which is 2. Notice how the square roots, or radicals, went away. Now, this also follows one of our rules here of a squared minus b squared. So that I have 3 squared minus the square root of 7 squared, which is 9 minus 7, which is also 2. And we can use that when we simplify something like 3 divided by 5 plus the square root of 2. Now if I take this and multiply by the conjugate on top and bottom, which would be 5 minus the square root of 2 on top and bottom, something unique here again happens. I am left with 3 times 5 minus the square root of 2 on top. And then on the bottom, if I use that perfect rule, we have 5 squared minus the square root of 2 squared. Well, I can distribute on top. 3 times 5 is 15, minus 3 times the square root of 2 is, well, just 3 square root of 2. Over 5 squared is 25. The square root of 2 squared is, well, just 2. So my simplified answer here, 15 minus 3 square roots of 2 all over 23. Now this lesson wouldn't be complete without one last bonus question. What if I want to simplify 2 over 4 minus the square root of 5? Now, I can again multiply by the conjugate on the numerator and the denominator. And in this case, since it's a minus square root of 5, we'll use the positive square root of 5. So 4 plus the square root of 5 on top and bottom, which means this is going to simplify into 2 times 4 plus the square root of 5 all over 4 squared minus the square root of 5 squared. So 8 plus 2 square roots of 5 all over 16 minus 5, which is 8 plus 2 square roots of 5 all over 11. And again, these are now simplified expressions because I do not have a square root or any radical on the bottom, and my radical on top is also simplified. That is it for this lesson on simplifying radical expressions. Good luck.